As everybody knows, heavier objects fall faster than lighter ones. Conclusion: actually falling is independent of weight? Conclusion: weight does matter? Conclusion: weight does not seem to be the deciding factor. This is a video where we look into how falling really works. Well, at least on the surface. Really though, this is a video about abstraction. Aristotle was not a physicist, but a philosopher. He did write the first book on physics, though. He wasn't just any random philosopher, though. He was the most influential thinker in the West from 300 BCE to around 1600. His views and explanations had reached such popularity and eminence that they were essentially considered to be the truth about the universe. Like the saying goes, in the absence of fact, opinion dominates. Aristotle held that things fall because they tend to their natural place in the universe, which for heavy things is the Earth. This is what he called a natural motion because it happened on its own by itself without any reason being necessary. Whereas a motion which is caused by a pulling or pushing force, he called violent motion. So in this worldview, you could say that heavy things fall because it is their nature to be on the ground. Furthermore, he qualified that the speed at which an object falls is directly proportional to its weight and inversely proportional to the density of the medium through which it moves. Or in simple words, heavier things fall faster than lighter ones, and things move faster through air than through water. Is this true? No. No. What he said was incorrect in the sense that it does not agree with experiment. However, it may be a bit unfair to read his statements in this precise mathematical fashion that we do today. Then why bother with it in the first place? Because what Aristotle said is still more or less what most people think intuitively about falling. Remember the last video? You are wrong. You're wrong about motion. Galileo Galilei was born in Pisa, Italy, in the same year that Michelangelo died. And he died the same year Isaac Newton was born. By many measures, he can be considered the first proper scientist in history. Throughout his life, he was fascinated by motion, by the different forms of motion, and he spent most of his life investigating them. The major obstacle he faced was technology, or rather the lack thereof. He obviously had no camera. Even measuring time was a real issue. And he had no ability whatsoever to measure either speed or acceleration, and at that time those weren't even well-defined separated concepts. Just a quick historical side note, because for some reason the only story people know about Galilei is that he supposedly dropped rocks from the Leaning Tower of Pisa to find out how falling works. This is, as far as we can tell, half true at least. So apparently he did do it, but way later in life, and just as a presentation and not as an experiment. As a true falling motion was too quick to properly measure back then, he adapted the situation to slow everything down. He used a ball rolling down an inclined plane. With this setup, he found a relation that held for different angles of incline, so he theorized it would also hold for a 90-degree angle, so a free fall. This relation was Galilei's law of fall. The distance traveled is proportional to the square of the time. Also, falling is independent of weight. Is this correct? Yes. Yes. What about the paper then? It clearly falls slower, so how can Galileo be correct? Well, he was the first to really differentiate between the effect and the perturbation. So, what is signal and what is noise? Which is a nice segue to the key point of this video: abstraction. I think it's safe to say that both Aristotle and Galileo were extremely intelligent people, so why did they come up with such wildly different conclusions? Well, mostly their approach was very different, because Aristotle was a philosopher, so primarily a thinker and secondarily an observer, but not an experimenter. To observe is to look at reality, but to experiment is to choose the reality to look at. And therefore, Aristotle only considered falling exactly the way it occurs in nature. He was, again, an observer, so he only dealt with the actual world around him and not some abstract cases that are imaginable but don't exist. Galileo abstracted the effect to its main component, which is falling, and additional disturbing influences. He was aware of friction and air resistance, or drag, and he noticed that this could affect lighter objects but had almost no bearing on heavier objects. What he realized was that there are always several things going on at the same time, but if you reduce one of those, the friction part, to an extent where it doesn't matter anymore, you get a very simple law for falling. All things fall the same way, regardless of their weight. Speed grows linear with time. The distance fallen grows quadratic with time. If you remove the air, a feather will fall with the same speed as metal. Galileo himself couldn't verify this at his time, but only a few decades later it was possible to create a vacuum in a tube and perform the experiment, which turned out the way that Galileo had predicted. All things fall the same. We even repeated it on the moon in the 1970s, because the moon has gravity but basically no atmosphere.
How about that?
Almost all effects we can observe are actually a composition of many different competing fundamental effects. So abstraction is one of the key features of all of science. All scientific models are based on idealizations and simplifications, and all models are just approximations. You take into account some things, but you also ignore a lot of other things at the same time. In fact, I've done an entire video about this, which you can check out here. Anyway, this was Galileo's great triumph, that he could see the world not just as it is, but also how it would be if it were different, if it were simpler. He was able to abstract. Okay, enough history lessons for now. Let's clean up and explain what we know today. First up, falling is due to gravity, the attractive force between, in this case, the huge mass of the Earth and the mass of an object, which will accelerate the object down to the Earth. In fact, free fall is defined as a falling motion where the only acting force is gravity. Strictly speaking, this will happen almost nowhere on Earth, as there will always be friction, mostly with air. The only place where you get free fall is in space outside of the atmosphere. In the absence of fluids like air, all objects are equally accelerated by gravity and thus fall with equal speed. The same is true when the influence of the fluid is so small that it is not relevant. If the fall happens in a fluid, then there will be additional effects: drag, buoyancy, thermal effects, wind or currents. This will influence the object according to its density, area, shape, etc. And of course, we can also go into more detail. We can take into account that we are located on a sphere, or rather a deformed geoid, and that it is rotating on a tilted axis, that gravity changes with distance and also depends on local distributions of mass. When watched from outside the rotating Earth, a falling object moves along a Kepler ellipse, until it hits the ground, of course. If you're interested in that, check out this link to my video about elliptical motion. And even all of this is just a simplification. The more correct version of gravity is Einstein's theory of general relativity, that posits that objects simply move on straight lines, but space-time is curved by masses. As it so happens, my very next video will be about this topic, so as soon as it's up, I will put a link in here. Why do objects fall at the same speed though? How does this make sense when heavier objects experience a greater gravitational pull? That's why they are heavier in the first place. Excellent question, and we will address that in the next video of this series, which will be about inertia. See you then.